Hello team, in this lesson we'll dive into virtual threads in Java 21 and explore how they enable lightweight, high concurrency programming. I'll walk you through the core concepts, show you how to create and run virtual threads, compare them to traditional threads, and highlight best practices for using them effectively in real-world applications. So here's what we'll be covering in today's lesson on virtual threads in Java. We'll start by introducing the concept of virtual threads and briefly talk about JEP 444, which made them a stable feature in Java 21. After that, I'll walk you through a quick recap of traditional Java threads, just to highlight their limitations and why we needed a better concurrency model. Then we'll move on to the motivation behind virtual threads and the broader goals of Project Loom. I'll explain how virtual threads are built, what carrier threads are, and how the JVM parks and unparks virtual threads to achieve massive scalability. Once we've understood the theory, I'll compare virtual and platform threads so you can clearly see how they differ in design, behavior, and performance. We'll also touch on structured concurrency, a modern approach to organizing concurrent code more reliably. Then we'll move into hands-on demos. First, I'll show you how to create and run virtual threads using both the low-level and preferred APIs. We'll try running parallel tasks with virtual threads, and then compare that directly to using traditional platform threads. You'll see the performance difference with your own eyes. After that, I'll explain how virtual threads handle blocking and non-blocking input-output operations, and what you need to watch out for when dealing with native blocking calls. I'll also show you how to detect issues like thread pinning, using tools like Enable Native Access and JCMD thread pin. Towards the end of the session, we'll explore why ThreadLocal is no longer a good fit in the world of virtual threads, and I'll introduce you to a better alternative, scoped values, as proposed in JEP 429. We'll also look at how to migrate legacy code that relies on ThreadLocal so that it works safely with virtual threads. By the end of this lesson, you'll have both a theoretical understanding and practical experience with virtual threads, and you'll be ready to start applying them in modern, scalable Java applications. Let's get started. Let's begin today's session with a brief journey into the world of threads in Java, both where we started and where we're going. In traditional Java programming, we've long relied on platform threads, which are essentially thin wrappers over native operating system threads. This model, introduced with Java lang thread type, served us well for many years. But as modern applications have become more and more concurrent, handling thousands, sometimes millions of simultaneous user requests, the limitations of this model have become painfully obvious. Platform threads are heavyweight. Each one consumes a significant chunk of memory, often around 1 MB per thread stack, and context switching between them orchestrated by the operating system is expensive. This overhead makes it nearly impossible to scale up to hundreds of thousands of concurrent tasks, especially in environments like high-performance web servers or microservices under load. Now you may ask, why are we still talking about threads? Isn't async and reactive programming the way forward? That's a valid point, and indeed frameworks like Project Reactor, RxJava, and others tried to work around these problems using callbacks and non-blocking APIs. But they come at a price: complexity. Code becomes harder to write, read, debug, and maintain. Enter Project Loom, a groundbreaking initiative by the Java platform team. And at the heart of Project Loom are virtual threads. With the official release of JEP 444 in Java 21, virtual threads became a final, stable feature of the Java language for Java version 21. They are designed to solve the concurrency bottleneck without sacrificing the familiar thread-based programming model. Virtual threads are lightweight, cheap to create, and allow us to write straightforward blocking code that scales. Code that reads like sequential logic but behaves like high-performance asynchronous systems. They decouple the notion of concurrency from the limitations of operating system threads. In essence, virtual threads represent a fundamental evolution in Java's concurrency model. They preserve the simplicity of synchronous code while enabling the scalability of asynchronous architectures. So, in today's lecture, we'll explore what virtual threads are, how they work, and why they might just be the most important shift in Java's concurrency model since the introduction of the thread class itself. Now that we have understood why we need a better model for concurrency, let's take a closer look at what virtual threads actually are and how they work under the hood. A virtual thread is a lightweight implementation of Java-lang thread, but unlike traditional threads, it is not tied directly to an operating system thread. Instead, it's managed by the Java virtual machine itself, in coordination with a small pool of so-called carrier threads. You can think of carrier threads as actual platform threads, the real threads provided by the operating system. Virtual threads are mounted on these carriers only when they are actively running, and they are dismounted when they are waiting, for example during a blocking I/O operation or a sleep call. This mechanism is what allows virtual threads to scale so efficiently. The JVM parks a virtual thread when it hits a blocking operation and then unparks it later, resuming its execution, possibly even on a different carrier thread. This idea of parking and unparking is central. It means that the thread's Java-level state is preserved and suspended, while the underlying platform thread is free to do other work. It's like pausing a movie and giving the TV to someone else without losing your spot. Now, you might be wondering, how is this possible technically? Well, virtual threads are implemented using continuations, a low-level control flow primitive that lets the JVM suspend and resume execution at arbitrary points, without relying on operating system mechanisms like kernel-level context switching. The continuation holds the call stack, and the JVM simply swaps it in and out as needed. That's why we say virtual threads are heap allocated, in contrast to platform threads whose stacks live in native memory. So how do virtual threads compare to platform threads in practice? The key difference lies in cost and flexibility. Platform threads are expensive to create, maintain, and switch between. Virtual threads, on the other hand, are so cheap that you can spin up hundreds of thousands of them without blinking. And this opens the door to a dramatically simpler thread-per-task programming model, even at massive scale. And this leads us to an exciting design principle introduced alongside virtual threads, something called structured concurrency. In traditional Java, threads are often created in an unstructured way, scattered across classes and methods with no clear relationship to the parent task that created them. This makes reasoning about concurrency, and especially failure and cancellation, much more difficult. Structured concurrency proposes a different approach. Child threads should live and die together with their parent. In other words, lifetime follows structure. If a task spawns subtasks, those subtasks should complete, or be cancelled when the parent completes. Java's structured concurrency APIs, introduced in preview in JDK 21, are designed to make concurrent programming more robust, readable, and predictable, especially when combined with virtual threads. So in summary, virtual threads are a new kind of thread, cheap, flexible, and designed for massive scalability. They rely on carrier threads and the JVM's internal scheduler, parking and unparking themselves as needed, and when used together with structured concurrency, they help bring order and clarity to the often messy world of multi-threaded code. Now, I'll proceed by sharing my screen and presenting the source code examples I've prepared for this lesson. I'm sure it will be easier for you to learn through practical examples. All source code is available in the attachments to this lesson. I encourage you to pull the code from the repository and try the examples on your own computer. And of course, if anything is unclear during the explanation or after the lesson, feel free to post your questions below the video. I'll be happy to answer them. Let's now move from theory to practice and see what working with virtual threads actually looks like in real Java code. We'll begin with the most direct and explicit way of launching a virtual thread using the method thread start virtual thread. This API is very straightforward. You simply pass in a runnable, and Java takes care of launching that task as a lightweight virtual thread. In our first example, we create a thread whose job is to print a simple greeting. Hello from a virtual thread. Although this is a minimal task, it serves as a clean illustration of how concise and natural virtual threading can be. We also explicitly call join method on the thread, just as we would with a traditional thread, to ensure the main thread waits for it to complete. This demonstrates that even though the thread is virtual, it still supports the familiar lifecycle operations: start, join, interrupt, and so on. However, in real-world applications, we usually don't manage threads manually. Instead, we rely on executors to manage the lifecycle of threads for us. That brings us to the preferred approach for using virtual threads at scale: the new executor's new virtual thread per task executor API. This executor creates a new virtual thread for every task you submit. Under the hood, it schedules them efficiently across a small number of platform threads. In our second example, we use this executor to run a simple task that returns a string after printing a message. We then retrieve the result using future get method. Again, nothing here is new in terms of how you interact with the API, and that's the beauty of virtual threads. They let us write familiar blocking code that now scales far better. Pay attention that I use executor service in try with resources block. As of Java 19, all executor service implementations extend auto-closable. This means that you can in fact use any executor, whether it's a fixed thread pool, a cached thread pool, or a virtual thread executor, inside a try with resources block. When the block ends, the close method is automatically invoked, which under the hood calls shutdown and awaits task completion. Now, in practice, this pattern is most commonly used with virtual thread executors, because they are typically short-lived and task-specific. Conventional thread pools, on the other hand, are often long-running and reused, so developers don't usually wrap them in try with resources, even though they technically could. So while the feature is general, its usage is contextual. Just because the API allows it everywhere doesn't mean it's always the most idiomatic choice. But for virtual threads, try with resources is not only safe, it's preferred. Now, let's push this a little further. Suppose we need to launch 100 parallel tasks, each simulating a bit of work by sleeping for 100 milliseconds. Traditionally, doing this with platform threads would have been expensive, if not outright dangerous, due to memory consumption and context switching. But with virtual threads, it's no problem at all. In fact, in this example, we use the same executor to launch 100 tasks in parallel, and each of them logs its task number and the thread it's running on. Even though all of these tasks are technically blocking for a short time, the JVM handles it gracefully by parking and unparking the virtual threads, allowing carrier threads to stay available for others. I added this sleep for 100 milliseconds to imitate blocking waiting operation. The result is both high throughput and clean, easy-to-read code. In this block of code, I'm conducting a simple but powerful benchmark to observe the real-world difference between virtual threads and traditional platform threads, particularly when handling large numbers of blocking tasks. In this benchmark, I'm measuring the performance difference between virtual threads and traditional platform threads by simulating a simple workload. I launch a number of tasks, let's say 100, and each task just sleeps for 100 milliseconds. Before submitting the tasks, I start a timer using system nanotime method. Then I create an executor using executor's new virtual thread per task executor method. I use a loop to submit all 100 tasks to the executor. Each task simply prints its thread and then sleeps for 100 milliseconds. I store all the future objects so I can wait for each task to finish using get method. Once all the tasks are complete, I stop the timer and print the duration. This gives me the total time it took for 100 virtual threads to run a blocking task. Next, I run the same benchmark again, but this time I use a fixed thread pool made of platform threads, and I size the pool using the number of processors I have. I use this number because in a platform thread model, the optimal number of concurrent threads for CPU-bound work is typically equal to the number of available processors. Adding more threads wouldn't make the system faster. It would just cause context switching overhead. I again submit the same number of tasks and wait for them to complete. Then I record the time and print the result. Let's now check the console to compare results. The difference is striking. The virtual thread version finishes much faster. Just compare these numbers. Virtual threads around 10 times faster than platform threads. That's because the JVM is able to schedule all 100 virtual threads concurrently, even though the machine only has, say, 8 cores. When a virtual thread sleeps, the JVM parks it and uses the carrier thread for other tasks. In contrast, the fixed thread pool can only run as many threads as there are cores, say 8 at a time. So it processes the tasks in 12-13 sequential batches, each lasting about 100 milliseconds, leading to a higher total time. Don't forget that virtual threads can also be used in web servers, making them significantly more efficient and scalable. In my Java course, Java from Zero to First Job, we also cover web development and the Spring framework. When we get to the section on Spring Boot, I'll show you how easy it is to apply virtual threads in your Spring Boot application, and how doing so can greatly improve its performance under load. Now that we have seen how virtual threads allow us to launch thousands of concurrent tasks with ease, let's pause for a moment and look under the hood, because there's a subtle but important detail we need to understand when working with input-output operations. You might wonder if we can simply use blocking code everywhere, like input stream read method or socket accept method, and virtual threads will just magically scale. Then why did we ever bother with non-blocking APIs in the first place? Well, the key lies in what I like to call the illusion of non-blocking, and how the JVM handles blocking operations internally. You see, when a virtual thread hits a blocking call, for example, it reads from a file input stream or waits on a socket using Java I/O or Java NAT, the JVM doesn't actually block the underlying operating system thread. Instead, it intercepts the blocking operation and parks the virtual thread, freeing the carrier thread to run something else. This is why things like thread sleep or input stream read methods work so well. The JVM knows how to handle them efficiently. The problem comes when a thread enters a native blocking state, like calling a method that goes through JNI, Java Native Interface, or using certain parts of the JDK like file channel map or some older JDBC drivers. In those cases, the JVM can't safely intervene. The thread is now really blocked at the operating system level, and so is its carrier, effectively defeating the scalability of the virtual thread model. We call this spinning the carrier thread. That's why, as developers adopting virtual threads, we need to be conscious of what kind of input-output operations we're doing. If you're dealing with blocking input-output operations, prefer the APIs that are designed to work well with Loom. For example, use HTTP client type, which is virtual thread friendly. Prefer asynchronous database drivers like R2DBC over legacy JDBs when practical. Use classes from NIO for input-output operations or asynchronous file channel instead of old-school blocking file streams for large-scale input-output operations. The JVM can make blocking code scale, but only if we give it the right kind of blocking to work with. So don't assume every blocking call is safe. Sometimes, what looks like an innocent input-output operation can quietly kill your scalability by locking up a carrier thread. And in highly concurrent systems, one blocked carrier thread can mean hundreds of waiting virtual threads. Be mindful, and your system will fly. Now that we have discussed the potential pitfalls of native blocking calls in the context of virtual threads, it's important to understand how we can detect and diagnose such issues in real-world applications. While most of the time virtual threads just work, there are situations, especially in more complex or legacy systems, where a virtual thread may unexpectedly pin a carrier thread due to some native operation. When that happens, performance may silently degrade, and we may not even realize why, unless we know how to look. Fortunately, the Java platform gives us a few tools to help us observe and diagnose pinned threads. One of the most powerful diagnostic options is the Enable Native Access set to all unnamed flag, which you can pass to the JVM at startup. This flag gives internal tools, such as JCMD, Java Flight Recorder, or even custom agents, permission to access and inspect low-level runtime details, including information about virtual threads and their interaction with native code. Without this flag, some of the introspection APIs simply won't give us the visibility we need. Once native access is enabled, we can use the JCMD tool, which ships with the JDK, to identify whether any carrier threads are being pinned. The specific command we're interested in is JCMD followed by process ID and then thread.pin. This command produces a list of carrier threads that are currently pinned by virtual threads. Each entry includes a stack trace that tells us what the thread was doing at the time it became pinned. If you see a virtual thread blocking on a native method, perhaps a JDBC call or a file system access through a native channel, that's a red flag. By analyzing this output, we can spot patterns. For example, perhaps a specific third-party library is pinning threads due to a native implementation, or maybe some low-level input-output operation in your own code is the culprit. Either way, JCMD thread.pin is an essential tool in your observability toolbox when working with virtual threads at scale. Let's now turn our attention to an important but often overlooked aspect of thread management, the use of ThreadLocal, and how its role has fundamentally changed in the world of virtual threads. Historically, ThreadLocal has been a convenient mechanism for associating contextual data with a thread, whether it was a user ID, a transaction context, a security token, or a locale. Developers often use ThreadLocal to avoid passing context explicitly through every method call. In the platform thread model, where threads were long-lived, often reused across multiple tasks, this approach was quite natural. However, with the introduction of virtual threads, this design becomes problematic. Why? Because virtual threads are cheap and short-lived. We create them per task, and they are often discarded immediately afterwards. As a result, using ThreadLocal for request-scoped data no longer makes much sense. The thread itself is the request. There is no reuse, no shared thread pool, and therefore no need to attach state to the thread's lifecycle. More importantly, relying on ThreadLocal in this context can introduce subtle bugs and memory leaks, especially when developers assume the thread persists beyond the task, which it doesn't. But there's another deeper issue. Virtual threads can be parked and unparked, suspended and resumed by the JVM, and when a virtual thread is parked, it might come back on a different carrier thread later. This breaks assumptions made by ThreadLocal, and it becomes even trickier with inheritable ThreadLocal, which attempts to copy context down to child threads. When a virtual thread is resumed on a new carrier, that inheritance is no longer predictable or safe. To address this, Java is introducing a more modern and robust alternative: scoped values, proposed in JEP 429. Unlike ThreadLocal, scoped values are explicitly declared, safely shared within a lexical scope, and are immune to the pitfalls of thread parking or reuse. They allow you to bind the value to the execution flow, not to the thread itself. That's a fundamental but much needed shift, especially in environments where threads are no longer stable anchors for context. So what should we do if we have legacy code that uses ThreadLocal for passing around context? The good news is that migrating to scoped values is usually a matter of refactoring. Rather than setting a value globally for a thread, we pass it explicitly into a scope. Java provides clean APIs to run tasks with a given scoped value, which encourages clarity and prevents hidden side effects. In short, the days of using ThreadLocal as a magic global map tied to a thread are coming to an end. In the world of virtual threads, context must follow execution, not thread identity. And scoped value is the tool designed to do exactly that, reliably, safely, and with full awareness of the realities of modern concurrency. That's all what I plan to discuss with you in this lesson. Let's recap what we've learned today. We explored the concept of virtual threads introduced in Java 21 through JEP 444 and understood why they were needed. We reviewed the limitations of traditional platform threads and how Project Loom aims to solve them. You learned how virtual threads are scheduled by the JVM and how they differ from platform threads in behavior and performance. Together, we created and ran virtual threads and compared their performance to fixed thread pools. We discussed how virtual threads handle blocking input-output operations and the risks of native thread pinning. We talked about tools like JCMD and Java Flight Recorder for diagnosing thread-related issues. Finally, we examined why ThreadLocal is no longer optimal and how scoped value offers a safer alternative for context management. That's all for this lesson. Thank you so much for your attention. Have a great day and see you in the next lesson.